Okay, let's wait for 2 more minutes. Let's wait for 2 more minutes before we start. Okay, I think we can start now. So let me stop sharing the QR code now. So stop sharing. Okay, so when is our test? Anyone? When is our test? This coming, is it 30th, right? This coming Saturday. Remember, the test is at 9 p.m. At night, not at 9 a.m. So because the official schedule is 9 a.m., but unfortunately, there's maintenance work on campus from 9 until the whole day, I guess. So that's why we move it to 9 p.m. 9 p.m. All right. So before we start, any question about the test? Any question about the test? Okay. If there's no question, let's start with the review. Okay. So I think okay, there's changes. If you look at assignment number 4, where is my uh, question paper? Okay, let me share the question paper. And okay, so this is the question paper. This is the question paper, and you take a look at the question paper. Question number 2, which is the truss element. In my problem, I have this incline support, which is 30 degrees. We recently had a meeting about the test, about test 1, and we found out that the topic of truss with incline support is not going to be on the test. Okay, it's not going to be in the test. So initially we plan to have this incline support in the test, but unfortunately because of there's no standardized notes ada lecturer guna notes yang lain, ada orang ni guna notes yang lain, jadi tak standardized. So the coordinator said, okay, so for this year we scrap the idea of having incline support. So what we'll do is we just have our typical truss, which is this kind of truss, where we do not have any incline support. For your information, this roller is either horizontal or vertical only. No such thing as incline surface. So this is for your last year question. Last year, exactly 1 year ago. So we'll be discussing about this. And the other thing is that we talk about this element connectivity table. So if you do I think the question will be given with the element connectivity table, which means you need to follow the element connectivity table on the question, given in the question. So if you do your own element connectivity table, there'll be penalty. You get penalized. I don't know how many marks, but there'll be penalty. Because the thing is, if you use your own connectivity table, what will happen is that your answer might be different from your intermediate answer. Your intermediate answer will not be the same as the marking scheme, the one who did the solution. So you might get the same answer at the end, right? Intermediate answer might be the same. So there's an issue here. The issue is that if you do not get the right answer and you do not use the connectivity table given to you, then you will not get any points, because it's really hard to track where you did your mistake because we want to give you partial answer, partial credits. But if you do not use the connectivity table given to you, then we will have a lot of variation of the solution. So they will be troublesome. For your information, we have about 400 students. We have 400 students, and the one who set the question will have to answer the question. So that lecturer will mark about 400 papers. Can you imagine? Dah lah nak raya ni. Okay. So please read the question carefully, read the instruction, and follow the instruction carefully. Okay. Follow the instruction. I think part of the instruction is this. Use 4 significant digits for all workings. Significant figures, bukannya decimal place, but significant digits for all working. I would prefer if you do more. Okay, for example, all the intermediate calculation, you carry 5 significant figures or significant digits, but at the end, you round it up to only 4 significant digits. So this is the instruction, and this one is also, if you do not follow this instruction, again, you'll be penalized. So make sure your answer is in 4 significant digits at the end, at least at the end, at the final answer, sorry, it says 3 significant digits. So your inner working, your intermediate working should be 4, at least 4, but your final answer should be in 3 significant digits. Okay, so this is okay, because I thought it is 4. So at least carry 1 more digits before the final answer. Okay, so that is some reminders to you. Please follow the instruction. Please follow the instruction. All right, so so let's go to assignment number 4. Assignment number 4. I think I give you an extended date for assignment number 5, but not assignment number 4. It seems that some of you did not make it to the due date, and a lot of excuses are given to me. Unfortunately, I do not accept any late submission. I will accept late submission if you tell me before the due date what happened. Okay, for example, sir, saya ada interview lah, so saya tak sempat nak buat, tak sempat nak hantar on your due date. Can I submit a few hours later? Then it's okay. Okay. Tapi masalahnya kat sini, all of you submitted after the due date, minta saya terima. I cannot accept that. Okay, because in real world, when you are doing work for your client, for example, I was working as a consultant before. Okay, when we have this kind of project, we always make sure we meet the deadline. Okay, we meet the deadline. If we cannot make it, we will call them beforehand. We call them beforehand and we tell them what is our problem, and they will hopefully accept. Okay, saya pernah balik kerja pukul 4 pagi, and then the next day lah, about 4 in the morning, and I came back to work at 6:30 in the morning, about 7 a.m. in the morning, and my engineers are asking me, boss, tidur kat sini ke malam tadi? I said, no, I went home at 4 a.m. and came back at 6:30. Okay, sampai macam tu sekali, because we need to basically meet the deadline. So here I'm training you to be a good engineer, but I'm not training you to give excuses. Please don't do this. Okay, if you feel that you cannot make it by the due date, tell me, because someone macam maybe ada valid reasons lah. Janganlah tak ada valid reason nak minta extension. Okay. Alright, so let's do this. Let's do question number 4. So why do you think I give you question 1 in assignment number 4? This is a very simple assignment here. This is a very simple question, number 1. But why? Why? Can anybody tell me why? Please say something, because I cannot read the chat screen. I cannot read the chat screen. So can anybody? Somebody? Nobody? Come on, please say something. So, why do you think I give you this question? Did you do this question? Did you do question number 1? Did you do question number 1? Okay, so I think since you are not cooperating with me, so I'm not going to tell you. Please read the textbook, okay? Please read the textbook. All right, so in this case, let's do question number 1. Okay, for your information, my assignment, when I give you assignments, there are some important points that I need to show you in the assignment. So if you cannot tell me what are the important points in that assignment, then something is not right. Okay, because especially some students yang copy, dia tak akan dapat what my point in that assignment. So the whole idea of this question is to tell you something very important when you do your analysis. Okay, so this is the basic. Number 1 is the basic understanding that you must understand to do your analysis correctly. If not, then if you don't understand this question number 1, or you cannot do question number 1, or you didn't get the point of question number 1, then I'm worried. Okay, anyway, since nobody is trying to answer my question, I just leave it to you that I assuming that you understand. Okay, so let's do this assignment number 4, question number 1. So the question is, what is the direction cosine of L and M for the element? Okay, so let's do this. So let me have a piece of paper here. Okay. Okay, so the question is this one. So let's draw the this figure here. So we have a bar in global coordinates, okay, and global coordinate x and y, okay, x and y, and this is node 1, and this is node number 2, and the coordinates of 1 and 2 are given. So let me have my global axis here. Uh-oh. Why is it not writing? Okay, so let me close my PDF here. Something is wrong. Okay, it's not giving me the authority to shut down that thing, so let's do the other way around. Mhm. Okay, so let's restart this. And I think I need to share. Okay, let's reshare. Okay, so let's draw. So this is the bar, and this is node 1, node 2, global, global node 1 and global number, node number 2, and this is my global coordinate system, which is x and y, and this is the coordinate for node number 1, which is 5, 8, and this one is 2, 4, 2, 4. So the question is asking us, what are the direction cosine L and N for the element? So what is L? What is L? And what is M? What is L and what is M? Anyone?
Cos theta.
Cos theta.
L is cos theta, right? So now the question is, where is my theta? M is of course sine theta. So the question is, where is my theta? Anyone?
At 1.
At 1. So it's here.
No. The other way around.
The other way. So which way? Remember that angle is always measured from the horizontal and counterclockwise, right? Counterclockwise. So in this case, my theta is here. Okay? So please, this is very important because when you choose the wrong angle, then everything will screw up. Okay? Everything will screw up. Note that if you read the textbook, this is how the convention is. This is how the convention is. So the angle is always measured from node number 1 from the horizontal and must be counterclockwise. Okay, so that is the standard. That is the convention. So and the formula is this. This is in your textbook. This is in your textbook. So now it's easy now. So in this case, if you just follow the formula here, then we should be okay. We should be okay. So LE is just the x2 minus x1 square plus y2 minus y1 square. Okay, and square root. So if you do this correctly, you should get 6.7082, and then of course L, which is cos theta, is just x2 minus x1 over L E. Again, this is from node 1 to node 2. Remember that. So in this case, x2 is 2 minus, I think this one is 5, 8. Okay, 2 minus 5 over 6.708, and you should get about minus 0.4472. Okay, so again, the same thing with M. This is just y2 minus y1 over LE, which is just 14 minus 8, this is 14, over 6.708, equal to 0.8944. Okay, is there any way we can check if our answer is not correct, but at least what we say logical? Okay, can we check that? Can we check? Note that theta is in which quadrant?
Two.
Quadrant 2, right? So what is positive in quadrant 2? Only sine is positive, right? In quadrant 2. So this is how we check. This is how we check. We know that at quadrant 2, cosine is a negative value, which is okay, we are okay. And at quadrant 2, sine is positive, which is, again, at least we know that we get it not the answer, I mean, not the numerical numbers, not the numerical answer, but at least we got the angle, the positive sign and negative sign correct. So this is one of the ways that we can check. Okay. And for example, if you did something wrong, for example, you take the wrong angle, this is maybe your theta, then you realize, oh, okay, this is only, in this case, this is less than 90 degrees, right? So this is, then you know this is wrong. Okay, this is how we check. So this question number 1 is basically telling us that you must correctly identify which are the angle. Okay, which are the angle. If you don't identify it correctly, then your L and your M will be incorrect, and everything will screw up. Everything will screw up. So now this is the easy part. Okay, so it asks us to draw the X or local or natural coordinate system. Okay, so in this case, let me delete this. So let me just draw it here. So in this case, our natural coordinate system is this one. Note that we use X bar for the natural coordinate system, yeah? X bar. So, and it asks us to redraw the element with Q1, Q2, Q3, and Q4. We note that this is Q1 prime because this is in the coordinate in the local coordinate system, and this might be Q prime 2. But what is the Q1, Q2, Q3, and Q4? So Q1 and Q2 correspond to the node 1, local node 1 displacement. So let's see if, let me redraw this here. So for example, this is before loading, and this is after loading. Okay, this is after loading. So we know that node 1 here originally, node 2 here originally, and after the loading, move node 1 move here, node 2 move here. So this is the, let me change color here. So this is the translation. So this is the Q1 translation, and this is the Q2 translation, and this will be our Q1 prime. And the same thing for our node 2. This is the horizontal translation, and this is the vertical translation, and this is our Q3, and this is our Q4, and this is 90 degree to the beam, to the bar, and this is our Q prime 2. Okay, Q prime 2. And the relation between Q and Q prime is just LM0000 LM. And of course, this is our Q1, Q2, Q3, Q4 equal to Q1 prime and Q2, Q2 prime. Right? So this is basically our next question, which is our next question. This one. So if Q is this value, what is this one here? So the question here is just, this is our Q prime, this is our Q. So what we need to do is just substitute what is L and N, L and M. So if you do this correctly, let me rewrite this 4472 0.89 or 40000 minus 0.4472 and 0.8944 times Q1, Q2, Q3, and Q1 and Q2 for the first row. This is 0.01 minus 0.025 and minus 0.05. This one should equal to Q1 prime, Q2 prime. Okay, so when you do this matrix multiplication correctly, you should get Q1 prime equal to 0.00894 and Q2 prime equal to minus 0.03541. Okay, so that is the solution. That is the solution for question number 1. So question number 1 is basically telling us that you must be very careful with your angle. Okay, so the convention is this. Okay, make sure that you understand this one. Saya takut nanti ada orang yang ambil sudut yang salah. Ambil sudut yang salah. Note that it must start with node number 1. So the angle is always measured at node number 1 from the horizontal in the counterclockwise direction. In the counterclockwise direction. So that is the point that I want to make there in question number 1. Okay, so I think I'm not going to do question 2 here, but what I'll do here is I'll do this one, which is the one from the test, the one from the past year test. Okay, we've done this before. So let's look at this question here. Let's look at this question. Okay, so note now this is very important. I need to show you some of the shortcuts. Some of the shortcuts that you might need. You might need. Okay, so let's read the question. A 4-bar planar truss structure as the geometry shown in figure Q2. The structure is supported at joint 1, 3, and 4. Okay, 3 and 4. These are basically our boundary condition. So this one, and this one are our boundary condition. And okay, a concentrated force of 20 kilonewton, which is this one, and an angle beta, which is 45, is applied to the stress structure. Each member of the structure is made of steel. So basically all the material, all members have the same material properties and has a cross-sectional area of 500 millimeter square. Okay, so same material, same area, cross-sectional area. So this is the coordinates. Why do we need the coordinates? Anybody? Why do we need the coordinates? So I hope you can see that this is for the sine and cosine calculation. That is for the sine and cosine calculation. Without that, then it's not easy to calculate the angles. So we need that because of the sine and cosine. Okay, so, and again, this is the element connectivity table. Note that in the element connectivity table, it will tell us which one is node 1, which one is the local node 1 and local node 2 for each element. Why do we need this? Why do we need this? Why do we need this? Anyone? Why do we need this? Why do we need the node numbers? The local node number. Why do we need that? Anybody? Nobody?
To find the global matrix. For the global matrix stiffness.
Before that, before the global matrix. Tak dengar. Can you say louder, please?
For local node.
Yes, we need local node numbers. My question is, why do we need local node numbers? Why is it important to know the local node numbers? See, saya baru cakap tadi. Why do we need that one? Because look at this. Hazrul nak cakap apa?
To determine the angle.
Yes, this one. Remember this. Remember this. We need to know which one is node 1 or node 2. If it so happen that our node 1 is here and our node 2 is here, so the angle is from here to here. It is not from here to here, okay? So this is why we need to identify the node numbers, the local node numbers, okay? So this happen every time I teach this class, student ada buat silap. Okay, I keep telling them before the test, remember this figure because this is what we use to determine the angle theta. Okay, once you know where is your theta, then you can calculate your L and M correctly. Okay, so in this case, this is our theta. That is why we need our node number, local node number, and our coordinates. Okay, and our coordinates for this. Okay, and of course for this. And the node number will determine where is our theta located. Is it here or is it here? Okay, so be very careful with this. Be very careful with this. Okay, we need L and M to calculate our element stiffness matrix, yeah? Element stiffness matrix. So be very careful about this. Be very, very careful about this, yeah? Kalau tak nanti a lot of points will go down the drain. Okay? Alright, so this is the one. So this is the one. So that is why we need to have this element connectivity table. So it is just not for the global stiffness matrix. The most important thing, this is for your angle theta. Okay, for each element. There are 4 elements, then you have 4 thetas for each element, yeah? So be very careful with this. Be very careful, yeah? Be very careful. Student always make mistake here. So remember this, okay? Remember this. Remember this. All right, so it says here sketch the finite element model, clearly label the nodes, element, degrees of freedom, and then determine the status of the degrees of freedom. Okay, so let's do part number A. Before that, I think let me find my solution first. I think my PC was shut down just now, so it was not. It's not here. So let me find my solution first. Yeah, let me find my solution. Okay, where is my file manager, file explorer? Okay, so okay, so assignment 5, question number 2. Okay, so I think if you look at, I think I given you, I shared with you the formula sheet, right? The formula sheet. I think you can use that for our problem here, for our problem number 2 here. Okay, so we need to draw the the element, every single one of them. So, all right. So, wow, my PC is very, very slow, eh? Okay, I have my solution here. Okay, so let's look at the question again. So this is the one. So sketch the finite element model, clearly labeling the nodes. Remember that in one of your exercises, in one of your assignments, I told some of you just do not have any finite element model. You didn't draw any of the model. So please, this is important because you need to draw this in the uh, in the test. So now let's look at question number 2. So this is question number 1. So we are done with question number 1. Let's look at question number 2. So it asks us to draw the finite element model. So we have element, this kind of element. So let me draw it a little bit huge so everyone can see. Okay, so in this case, we need to number all the element, to all the elements. So if you look at the question paper, I hope you have your question paper with you, because element number 1 is node 1 and node 2. So in this case, okay, let's number the node 1, 2, 3, and 4. So this is element number 1, and element number 2 is node 2 and 3. This is element number 2, and element number 3 is 3 and 4. This is element number 3, and this is element number 4. Okay, so this is the numbering, but I think the question asks more than that. It says that sketch the finite element clearly or labeling all the nodes and the element. Okay, we done all this, and degrees of freedom. Yeah, degrees of freedom. So how many degrees of freedom do we have here? Okay, so let's look at our degrees of freedom. So let me change pen color here. So will not confuse you. So note that the numbering system, Q1 is always the horizontal, even is for the vertical. Q1 and Q2, this one is Q2, so we have Q3 and Q4, and this one is Q5 and Q6. Of course, this one is Q7 and Q8. So that's the degrees of freedom. And what else? What else is also say degrees of freedom? Okay, that's it. That's it, degrees of freedom. So note that here, okay, there are how many Qs? There are 8 Qs, right? So which means our global matrix, our global SLE matrix is what size? What is the size of our global? Berapa?
8 by 8.
8 by 8. Wow, this is huge. But note that even though the degrees of freedom in this question is 8, because we have 4 nodes, so it means we have 8 unknowns. But because of the boundary conditions, the number of unknown will be reduced. So what are the boundary conditions here? What are the boundary conditions here? Can anybody tell me what is the boundary condition here? Look at the question paper. So what are the boundary conditions here? What are the boundary conditions?
Pin join
Pin join
1 and 3.
1 and 3. So what are the boundary conditions for pin joints?
Q1 equal Q equal to
So
0.
basically, both of them, the horizontal and the vertical displacement, are zeros, right? So in this case, this is 0, this is 0, this is 0, this is 0. Okay, so that's the pin joint. How about any other boundary conditions? Okay, we done this. We done this one. So any more? Okay, so in that case,
Q7
Q7
is 0.
equal to 0 because there's no horizontal displacement, right? Because it cannot move in the horizontal direction, but it can move up and down, which is vertical. So which is vertical. So now initially we have 8 unknowns. Okay, 8 degrees of freedom. Now, after we put all the boundary conditions, how many unknowns are there?
3.
Only 3, right? So don't worry, don't worry. Tengok, mula-mula tengok soalan. Oh, banyaknya notes. Okay, banyaknya notes sampai 8. Tapi when we put on all the boundary conditions, we are only left with only 3 unknowns, which means our reduced SLE is going to be what
3 by
size?
3.
3 by 3. So 3 by 3 senang. Yeah, it's very straightforward, kan? How to solve a 3 by 3 SLE, right? So no issue here, no issue. So please, do not get afraid or do not get intimidated because of the questions. So in this case, it is just a 3 by 3 matrix, which only 3 unknowns. In this case, our unknowns are Q3, Q4, and Q8. Okay, Q4, Q3, and Q3, Q4, and Q8. The rest are boundary condition, because the boundary condition all of them are zeros, right? In this boundary condition. So when the boundary condition are all zeros, we call this homogeneous boundary condition. But remember in assignment, I don't remember the assignment, bar assignment that we have, I think one of the boundary condition is 2 times 10 to the minus 5 millimeters. That is what we call a non-homogeneous boundary condition. It's a boundary condition, but it is non-zero. It is a non-zero boundary condition. So in this case, the boundary conditions are all zeros. So we call this a homogeneous boundary condition. Okay, so what next? What's next? So what is next is ask, okay, then determine the status of the degrees of freedom. So the status of degree of freedom is only Q3, Q4, and Q8. So basically, it's a 3 by 3. And then set up the reduced stiffness matrix. Okay, this is something new. What is meant by reduced element stiffness matrix? What does it mean by reduced stiffness matrix? Okay, can anybody answer me? Saya minta maaf, batuk saya masih lagi tak hilang. Walaupun saya dah tested negative for COVID, but the after effect of batuk tu is still there. Okay, so what is it meant by reduced element stiffness matrix? Anyone? What is meant by reduced matrix? Reduced matrix. Okay, never mind. Hold that thought. Let's try to do element by element. Let's try to do the element by element. So now, note that we have the element connectivity table and so on. So let me try to okay, so this is the malas nak tulis so saya pun just masukkan aja lah. Okay, so this is the question punya. This is from your question. This is from the question. Okay, so what we need to do is to find the element stiffness matrix. So the standard procedure is always to find the element stiffness matrix. And the question is, what is the element stiffness matrix formulation? So again, let's add up here. This one. Okay, so this is the formula. This is the formula for our element stiffness matrix. Element stiffness matrix. Note that this formulation requires that we have L and M. L and M. So we know what is EA. Element is the same, A, L. But now we need to know what is all this LM. And note that for every element, they are different. They are different because the angle will be different, which means L and M are different for all the elements here. For all the elements here. So let me clarify. This is for your K element. K element here. All right. So, what do we do here? What do we do? Okay, so let's start one by one. Let's start with one by one. So let's say element number 1. Before that, we know that our formulation requires that for example, our L, which is our cos theta, will require that x2 minus x1 over LE. So what is the LE? What is LE? So LE for each element, LE for each element. So, and then our M will be sine theta equal to y2 minus y1 over LE. And note that for this formulation, let me change color. Note that this is for node 1, node 2. Sorry, bukan node. This is for displacement 1, displacement 2, displacement 3, and displacement 4, which is correspond for this one. Node 1 has 2 displacement, right? 1 and 2. Node 2 has 2 displacement, 3 and 4. So this is the numbering. This is the numbering. And note that this is only for element, which is local. Because in our case now, let's see element number 1. So for element number 1, which is node 1 and 2, node 1 and 2. And okay, so this is element 1. So which one is node 1? Which one is node 2? Local node 1 and local node 2. So which one? So we have to look at the nodal connectivity table or element connectivity table, which is now 1 and 2. The first node of element 1 is global node 1. The second node of element 1 is node 2, which is this one. So according to that element connectivity table, this is our node 1 and our local node 2 for element number 1. And do we have the coordinate for node 1 and node 2? Of course, we have 0, 0 and 3, 0. So in this case, our node 1 is node 1 is 0, 0, and our node 2 is 3, 0. Is 3, 0. Okay, so can we find what is our LE? LE is straightforward. You can just, if you want, you can use x2 minus x1 square plus y2 minus y1 square and square root. Or from inspection, we know that our LE is just 3, right? Our LE is just 3. Our LE is just 3. And what about our theta? What is our theta? What about our L, which is our cos theta, which is x2 minus x1 over LE. So remember that our theta is always measured from node number 1, right? From node number 1 and measured from horizontal in the counterclockwise direction. So in this case, this one should be by inspection, our theta should be here, right? At node 1, right? So this is 0. Sorry, cos theta is not 0. Cos 0 is 1, right? And M is sine theta. Or to be safe, let's calculate this. What is x2? X2 is 3 over 0. So 3 over 0, which is cos theta. Cos theta is cos theta. Sorry. Am I getting this right? 1 1 and 3 0. So no, L is not 0. X2 minus x1 is 3 and LE is 3. So this is equal to 1. And sine theta is, of course, there's no elevation, which is 0 over 3, which is 0. So now we know, that our theta is right here on node number 1, and cos theta and sin theta is 0. Okay, so this is basically the setup thing. So we know what is our L, length of the element, our cos theta, and our sin theta. What is next? What is next? What is next? This one. What is next? Is this one. Oh, man. All right. So how do we go about this? How do we go about this? Okay. Before that, let me just put what is AE. AE, according to the question, is 500 millimeter square, right? Or 510 to the minus 6 meter square. So the best practice, normally in my case, when I do finite element analysis, I'll always set every unit to the basic unit. For example, instead of millimeters, I use meter. Instead of kilonewton, I use Newton. So it's easier to keep track. So in this case, our AE is 500 times 10 to the minus 6 meter square, and our E, Young's modulus for each element, is 200 gigapascal. 200 gigapascal. Gigapascal. So I'm using every single unit. Okay, basic unit. Pascal is just Newton per meter square. Newton per meter square. Okay, now what is our K matrix? Element stiffness matrix for first element here. Note that I put a bracket. Bracket. Macam mana ni? So note that this is a lot of calculation. This is a lot of calculation. Okay, and I think because of that, that is why if you look at the question paper, it is asking us to do a reduced element stiffness matrix. Okay, because to save you time, But there's a but, there's a but, there's a but. Never mind about the but first. Let's finish these two. Okay, so how do we do this? Note that from the picture, from the figure, we know that Q1 and Q2 is equal to 0, which means in this case, our Q1 and Q2 is equal to 0 for element number 1, then we know that we are not going to need this and this. Am I correct? Betul tak? So do we need to calculate this value and this value? No, because that will be 0, because any number times 0, because if you when we put here example Q1 and Q2, and Q1 and Q2 is equal to 0, so we do not need this. We do not need this column here, because anything, this column times Q1 will be 0 because Q1 is 0. The second column times Q2 will also be 0 because Q2 is 0. So column 1 and column 2 will not be needed for element 1. And the same thing, this row and row will not be needed, because remember that we have 4 unknowns here, but 2 of them are already known. So what we are left with only 2 unknowns. So what we need is only a 2 by 2 matrix, a 2 by 2 matrix. So in this case, okay, so you need to plan this carefully, yeah? Identify everything. So in this case, what we need is only Q3 and Q4 here. So this is the matrix that corresponds to Q3 and Q4. So I do not want to go to the calculations. So what I get here is, I'm sorry, because basically I cheated. Yeah? So this is the reduced K1 matrix. If you do this correctly, what you get is a 3.333 0, 0, 0, 10 to the 7. Or to make it very clear, for clarity, 7. Okay, so this is element number 1. And note that this corresponds to global node 3 and 4. Global node 3 and 4. Betul tak? Global node 3. Global node 3 and 4 here. 3 and 4. Because this is not calculated. We only calculate this one, Q3 and Q4. So let me, this is 3 and 4. And basically this is row 3 and row 4. So I normally omit this 3 and 4 because I'm so used to this. So maybe you might want to include the row numbers and the column numbers. But for me, doesn't matter. Okay, for me doesn't matter. Note because this is reduced because of our BC. Okay, BC is that Q1 equal to Q2 equal to 0. So that is the element number 1. Element number 1. So okay, so we do the same thing again for element number 2, element number 3, element number 4, and so on. So now let's do element number 2. Element number 2. I'm not going to show everything, but I hope you get the idea here. I hope you get the idea here. Element number 2 is node 2 to node 3, which is this one. Okay, node 2 and node 3. And if we draw the element, we know that this is node 2, global node 2, global node 3, which means according to this element connectivity table, first node of element 2 is node number 2, global node 2, and second node of element number 2 is global node number 3. So basically, this is our node 1, and this is our node 2. And where is our angle? Our angle is here, theta. This is important. This is very important. Okay, so that is the angle. That is the angle. So now we know what is our node 1 coordinate and our node 2 coordinate. And we can find our, of course, our LE. Okay, I think I have my solution here. So my solution says that my L is, oh, sorry, let me just put here length of element number 2. This is length of element number 1. This is length of element number 1. I don't know kenapa dia tak nak padam. Never mind. So this is 5. So the coordinate now is node 2 and node 3 coordinates, which is 3 and 0, 0 and minus 4. Okay. 3 and minus 4. 0 and minus 4. Sorry, 0 and minus 4. 0 and minus 4. So L2 is 5, and note that my L cos theta should be a negative number because This is negative for both sine and cosine. And this quadrant is both, quadrant 3 is negative for both sine and cosine. So I think I should get a negative number. Negative 0.6, and m is negative 0.8. Negative 0.8. And now, again, do we know the boundary conditions here? So again, we need to find the reduced stiffness matrix. So what is our K of element number 2? And note that if we are going to do this, we know that at node 2 here, the boundary condition is this point here. Q5 and Q6 is going to be 0, right? So for element number 2, if we look at the full stiffness matrix, this is not global node 1. This is global node number 2, global number 2 and global node number 3. So this is Q3, Q4, Q5, and Q6. And we know that 5 and 6, okay, boundary conditions, Q5 equal to 0, Q6 equal to 0. So 5, okay, so we know that 5 and 6 are not going to be useful because any numbers time Q5, which is 0, then is equal to 0. And because instead of having 4 unknowns, we are only having 2 unknowns. So what is our interest is only this element here, is this element. So in my case, what I have here is 7.2, 9.6, 9.6, and 12.8 times 10 to the 6. Okay. Note that this is my reduced K matrix. Reduced K matrix. All right. So again, repeat the whole thing again. Repeat for element number 3, but I'm not going to do that. But what I'll do is I'll give you my solution, and hopefully you get the same as mine. The same as mine. Okay. So element number 3. Okay, element number 3. Okay, let's look at element number 3. So what is element number 3? This is element number 3. Again, at element number 3, this is boundary condition. So we only have Q7 and Q8. Q7 and Q8. So my LE for element number 3 is 5. My L. Okay, so note, where is our angle here? Node 3, node 4 global. So node 3, node 4. So our angle is here at this point here. At this point. So this is our angle theta here. So our L, my L here is 0.8. Note that this quadrant, everything is positive. Sine and cosine are positive. M is 0.6. And my K matrix for element number 3, note is only a 2 by 2 because at this point the boundary condition is Q5 equal to Q6 equal to 0. So in this case, what I have here is only 7 and 8. 7 and 8. 5 and 6 are zeros. 5 and 6 are zeros. So when I do that, oh, sorry, there's one more here. Q7 is also 0, right? Yeah, Q7 is also 0. So it's only 1 by 1 matrix. So since Q7 is 0, what I have is only node 8. Yeah? What I have here is only Q8. This one. So this is wrong. So this is wrong. This is wrong. So what I have here is only one number, which is 8, which is 7.2 times 10 to the power of 6. Okay? 7.2. So element number 4. So where is element number 4? This one, element number 4. And note that element number 4, 2 and 4, and element 2 is the first, element number 4, 2 is the local first node, and 4 is the second local node. So my angle is theta is here, theta is here. So my LE for the fourth element is 1.4142, and my L, note that in this quadrant, only cosine is positive, only cosine is positive. And then my L, which is cosine, is positive 0.7071, and sine is a negative, and is negative 0.7071. And what are the boundary conditions here? The boundary condition is that for this, we know that Q7 equal to 0. Only one, only Q7 is 0, because if you take a look, Q3 and Q4 is non-zero, but Q7 is 0. So we have 1, 2, 3 unknowns. So our matrix is going to be a 3 by 3. A 3 by 3. Yeah? So in this case, element number 4. Note that for element number 4, we have 3, 4, 7, 8. But note that 7 is not going to be used because the boundary condition is 0. So this one is 0. So we are left with only a 3 by 3. A 3 by 3. So K4 is now this, which is 3.536 minus 3.536, and then 3.536. Okay, and then of course this is minus 3.536, 3.536 minus 3.536, 3.536, okay, minus 3.536, and 3.536 times 10 to the power of 7. 7. Okay, so now we have all the stiffness matrices for all the elements. Note that your element stiffness matrix, the diagonal is always positive, always positive. This is another way of checking, another way of checking. Please double check, please double check. Please double check. Okay, so I think if you look at my K matrix, are all positive, diagonal are all positive. So this is positive. Okay, this is also positive. Okay, so please double check that one. And of course, this is only positive number. This is only positive number. Okay, note that this is 348, 348, 348, Q3, Q4, and Q8. Okay, so 7 is not used. So now, the next thing to do is, let's look at the question again. It asks to do, okay, write the reduced system of linear equation in form of KQ equal to F. KQ equal to F. Okay, so now we need to find the global stiffness matrix. The global stiffness matrix. So let's look at the global stiffness matrix. And before we look at the global stiffness matrix, let's look at our, sorry, this one. Let's look at our degrees of freedom here. Our degrees of freedom. Okay, so our global degrees of freedom are only Q3, Q4, and Q8. Note that just now we mentioned that it's going to be a 3 by 3 matrix, a 3 by 3 matrix, global matrix, after we reduce everything. So this is a strategy, because I think time is very valuable in your test. So be very careful about time consumption. So now, so what we want to do is to find the global stiffness matrix. Okay. Oh, sorry, reduce global reduce stiffness matrix. Global reduced stiffness matrix. So what we have here is our capital K, our global, but now it is reduced. And note that for our global reduced stiffness matrix, we are only interested at degrees of freedom 3, which is Q3, Q4, and Q8. And definitely there will be only 3 rows that correspond to 3, 4, and 8. So note that for node number 3, global node number 3, we have element 1, element 2, and element 4 sharing. Node 2, global node 2 is shared between element 1, element 2, and element 4. So we expect that our global stiffness matrix here will have element 1, element 2, and element 4 contributions. Okay? So we have to remember that when we do bar element, overlapping point between element 1 and element 2. But now we have 3 elements overlapping. 3 elements overlapping. So if we take a look at element number 1, if we look at element number 1, so this is one of them. This is one of them, 3.33. Okay, 3.33. And then element number 2, this is 3 and 4. So this is another one. Okay, and element number 4, this is the other one. So we have 3 contributions. 3 contributions. So in this case, what we have here is, let me use a different color, non-standardized here. Okay, so this is 33.33 from element number 1. I'm using 33.33 because I'm going to use 10 to the power of 6. Because this is element 1 is 33.33, 10 to the power 7. 10 to the power 7. So 33.33, 10 to the power of 6 plus, okay, that's element number 1. How about element number 2? Element number 2, where is it? This one, 7.2 times 10 to the power of 6 plus 7.2 plus element number 4, 35.36. 35.36. Okay, so this is how you keep track. This is how you keep track of your overlapping point. 7.2. So let's move this somewhere. So this is element number 4, degrees of freedom 4. So let's look at number 4. 4 is again the same thing. 1, 2, and 4. Element 1, element 2, and element 4 is sharing at node 3, degrees of freedom 3 and degrees of freedom 4. So element 1, nothing. Element 1, nothing. No contribution. Element 2, 9.6. So it's going to be 9.6, 10 to the power of 6 plus element 4, which is 35 minus 35, minus 35.36. And then what about node number 8? Okay, node number 8. Let's look at node number 8. Okay, it's only element 4 and element 3. Element 4 and element 3 sharing the same node. So element 3 is this. Okay, 7.2. Oh, sorry. Sorry. So this is, sorry, I missed another important point here. So this is row 3, element number 8. Sorry, row 3 and 8. This one is 4 and 8. So if you look at this one again, as we look at note number 1 just now, this is 3 and 3, 3 and 3, 3 and 3, 3 and 3. So it's 3.33, which is this one. Element number 2 is 3 and 3, again 3 and 3, which is 7.2. And element number 4, again 3 and 3, this is 3, 4, 8, which is 35.36. And 4 and 3, this one is 3 and 4, 3 and 4 for element number 1. 3 and 4 is 0. 3 and 4 is 9.6 for element number 2, and for element number 4, 3 and 4 is 35.36. This one, yeah. And number 8, 3 and 8. Do we have 3 and 8 here? 3 and 8. 3 and 8 is this one, 3 and 8 is this one, which is 3.536. And what other element is sharing node 8? Element 4 is done. Element 3. Element 3. This one is 8 and 8, 8 and 8. 8 and 8. So 8 and 8. 8 and 8 is this one here, yeah? This one, which is, let me double check. 3 point, this one should be 35.36 times 10 to the power of 6, yeah? I'm sorry, this one should be 35, not 3.5. Okay, so we are done with the first row. And then let's try with the second row. Second row is 3 and 4, element number 1. Okay, this one. 3 and 4, which is 0, no contribution. And then this one, element 2 is 9.6, 9.6. And then element number 4, 3 and 4 is minus 35.36. Okay, we are done. Now with 4 and 4, and let's look at node 4 here. Global node 4 here, 4. Okay, 1, 2, and 4. So 4 and 4. 4 and 4 for element moment is 0, nothing. This one is 12.8 for element number 2. So this one is 12.8. And then for element 4, 4 and 4 is plus 3.5, 35.36. And then 4 and 8, 4 and 8 is minus 35.36. Okay, and then let's look at 3 and 8. 3 and 8, 3 and 8 is possible only for which element? 3 and 8, this one, 3 and 8. Oh, this one. 3 and 8. 3 and 8 is only possible for element number 4. This is 3, this is 8. So it's only possible for element number 4. So basically, we can just reuse number 4, which is now 35.36 minus 35.36. And this should be times 10 to the power of 6. So when I redo this, my K matrix is now, okay, when I simplify that, this is going to be 7.589 minus 2.576, 3.536 minus 2.576, 4.816 minus 3.536, and then 3.536 and minus 3.536 and 4.816 2, 5, 6. Now this is 10 to the power of 7. Again, take note that the first thing is that my diagonal is positive, and then it should be mirror. Mirror. This one and this one the same. This one and this one the same. This one and this one are the same. So this and this are the same. This and this are the same. This and this are the same. Symmetric. Symmetric. My K is symmetric and diagonal is positive. So this is my K matrix, global stiffness matrix, global reduced stiffness matrix. Right, so we know it's a 3 by 3 because we have only 3 unknowns. 3 unknowns. So what about the force vector now? What about the force vector? Look at the force vector. So, I don't have the picture here. Where is the question paper? So, okay, so we have only this one, right? At node 2, right? So we have Q3, we have F3 and F4. We have F3 and F4. So in this case, what we have here is our force vector. Okay, force vector. Our force vector is only F3, F4, and 0 because we do not have F8. We do not have F8. So this is 3, 4, and 8. So there's no such thing as F8 here because look at this. This is only F3 and F4 and none at F8. So this is what we get. This is what we get. Okay. So what is F3? F3 is just 20 kilonewton cos beta, right? Cos beta. And F3, F4 is just 20 kilonewton sine beta. So if I substitute that into the equation, this becomes this, this becomes 1.4142, and of course because this is 45, sama je, times 10 to the power of 4 newtons, Newton. So solve for the solve for Q3, Q4, and Q5. So we know that now this is K matrix times Q must equal to F n. Solve for the unknown, which is Q3, Q4, and Q8. So I'll leave it to you to calculate this. And what I got here is Q1 equal to 2.49 times 10 to the minus 4 meter, or this is basically 24.9 millimeter. Okay, not Q1, sorry, not Q1, Q3. Q1 is 0. Q4 is equal to 7.05 times 10 to the minus 4 meter, or 70.5 millimeter, and Q8 is equal to 3.79 times 10 to the minus 4 meter, or 37.9 millimeter. Okay, so that is the solution. That is the solution for question number 2. Question number 2. Okay, so I didn't go to the details, but at least I give you the framework. So what you can do here is you might want to try on your own. Our test is 3 more days. Okay, so you can try and do this. Hopefully you get it right. Okay, hopefully you get it right. So that is one of the questions. So we are done with this. So we are done with part D. Now there's another question that we need to calculate. Calculate the reaction at joint 4. Okay. Join 4. So in this case, what we need to do is we need to calculate the the remember that when we did our K matrix, that we cancel the one that but when we did that, we we eliminated reaction is this one. So we eliminated R7 here, R7 and R8 because you know that we have R7 and R7 because Q7 is 0. When Q7 is 0, automatically we have R7 automatically. The same thing with Q1 equal to 0, automatically we have reaction at that point. The same thing for Q2, then we have R2, and the same thing at Q3 equal to 0, then we have R3, and Q4 equal to 0, then we have R4. But in this question, it's asking us only to do one of the reactions. One of the reactions. Okay, so how do we do this? Okay, there are other ways to do this. What I did just now, I was basically doing what I did for my elements is that I basically eliminated, I reduced everything. I reduced everything. So instead of, note that what we need here is an equation that has the R7 terms there. Okay, so let's look at the overview first. Note that when we are doing the full matrix, for example, okay, we have 1, 2, 3, 4, 5, 6, 7, 8, and of course we have Q1, Q2, Q3, Q4, Q5, Q6, Q7, and Q8. So this is we are doing it the full matrix. Now we have about 8 by 8 matrix and a lot of calculations. Because the matrix is huge. It's an 8 by 8 matrix. So what we can do here is what we want here is, and of course we have our F here. So what we have here is only 0, 0. This one we have 1.1412 just now, Q3 and Q4, right? Is it? This one, sorry, this one, yeah, okay. 3 and 4, 3 and 4. And then we have the rest are 0, 0, 0, 0. Okay, note that when we know that Q1 is equal to 0 because of the boundary condition, automatically we are introducing reaction 1. Okay, we know that Q2 is equal to 0 because of the boundary condition, then we are introducing R2 in our SLE. Okay, Q3 is it's not a boundary condition, so there's no reaction for Q3 and Q4. Q5 and Q6, Q5 and Q6 is also not a boundary condition, and it has sorry, double check. Q4 and Q5, okay? No, Q4 and Q5, it's not a boundary condition. So now this is again 0, sorry, 4, 1, 2, 3, 4, 5, and 6 are 0. But Q7 is a boundary condition, which is 0. So we have R7. And Q8 is not a boundary condition. So this is 0. No, this is the full, complete SLE. But now what we want to do is we want to find R7. So we need this. We need this row. We need this row of the equations. Okay, we need this row of the equation. So this is the row that we need. Okay, this is the row that we need. Okay, so now we know that So we need to find all this. We need to find what is this term here, this term here, this term, this term, this term, this term, and all this term. All this term. Okay? So how do we do that? How do we do that? Okay, one of the ways is to look at the matrix. So look at the matrix for one thing. The other thing is, before we look at the matrix, let's look at the element. Let's look at the element here. So which one is R7? R7, okay, is here, right? This as R7, yeah? So of course, when Q6 equal to 0, then we have R6, Q5 equal to 0, then we have, okay, R5. So I think I make a mistake just now. I make a mistake. So this one, okay, so Q5 and Q6 is 0, right? Q5 and Q6 is 0, right? Q5 and Q6 is 0. So, okay, excuse me, this is 0 and 0. So that we have R7, sorry, R5 and R6. So we are only interested at R7. Look at R7. So R7 only involve these two elements, element 3 and element 4. Element 3 and element 4. So what we can do here is we can use this, and we know that this is only involve element 3 and element 4. Element 3 and element 4. And note that what are the points here. So this is our Q5, Q6, Q7, Q8, and Q3 and Q4. Okay, so okay, so what we can do here again, Q5, Q6, Q7, Q8. Sorry, not Q. This is wrong. Element 2, element 4. Element 4 here is Q3 and Q4. Q3 and Q4. And then element, this one, element 3 is 5 and 6. 5 and 6. And then 7 and 8. Okay, so this is the what we want, what we want, because it involves only element this element 4 and element 3. But again, okay, note, but again, Q5 and Q6 are zeros, and Q7 are all zeros. So we do not need that. We only need 3, 4, 8. 3, 4, 8. Okay? Because the rest are 0. Any number times 0, Q5 is 0, Q6 is 0, Q7 is 0, then we have no use. We have no use. So let's look at this. And 3 and 4, element 3 and 4 is element 4. Element 4 is 3 and 4 for must equal to 0 equal to 0 plus R7. Okay, the one that involves 7, row 7, 3, 4, 8. Okay, row 7, 3, 4, 8. So let's look at row 7, 3, 4, 8. Okay, so we can see here, okay, row 7, you have to calculate row 7. So in my case, I have calculated that. So row 7 is, okay, you have to take a look at this formula for the row 7. So let me give you my solution. And this is minus 3.0 35 35.36 lah ya. 35.36 35.36 and then this is minus 35.36 plus 9.6. So what we have here is 35.36 and okay, so let me cut it short. So R7, if you do this thing correctly, what you get is 35.36 times 10 to the power of 6 times Q3 is this one, okay, plus Q3 times plus 35.36 times Q4, okay, this one times Q8, and what I get here is 66.36 times 10 to the power of 3 Newton, kilonewton, 6.36 kilonewton. Okay, and the next question is this one. Okay, so determine whether member 2-4 is in tension or compression. So element 4, this one, this one. So what we need to do is to find the stress. The stress. So we need to find the stress. So the formula for stress is just sigma. I think this is in your formula sheet. And note that we are interested in only element number 4. Okay, and now this is minus L, minus S, minus M, L, and M. And of course, these are all for element number 4 and Q3, Q4, Q7, and Q8. Note that Q7 is equal to 0, so we do not need this one. So this should equal to, okay, we know already what is L4, we know what is minus L. This is confusing. This is the element, This is the element, but this is the sine, cosine, So let me change the sign here, because L is used, So C4 cosine, minus S4 sine, and this one is C4. So this is L for the length of the element. This is, just now I was using L4 too, so this is confusing. So instead of using L, I'm using C for cosine. C for cosine, and what I have here is 7.71 times 10 to the power of 6 Pascal. So this is 7.71 megapascal, and it is in tension. Okay, so if you look at this question, actually it is this is tedious in a way that you must keep track of all your elements, of all your the number in your matrix. Because if you do a full matrix, it'll be crazy. It'll be huge. The matrix will be huge. So by the way, we are not going to use all the numbers in that element, in that matrix. So that is why we are doing the one suggested in the question paper, which is set up the reduced element stiffness matrix. Set up the reduced element stiffness matrix. Okay. All right. So I think that's it for this assignment. So do we still have time? Okay, we still have about a few more minutes, because I think our class should end at 4:40, and now this is only 4:39. Okay, any question? Any questions? Okay, if we do not have any question, so I think we can stop this session now. And And before we do that, let me unstop sharing. Stop sharing. And okay, if there is no question, I think that's it for today. Okay, guys, good luck. Selamat berpuasa and selamat Hari Raya. Do we have class next week? No class, right, next week? Because next week I think is Hari Raya. Okay, so that's it for now. Thank you very much.
Thank you, brother. Thank you, sir. Selamat Hari Raya.
Thank you, brother.
Sama ya,